Fermat's last theorem, the simpleton's mathematical truth machine. My motto, plain honesty, simple truth, easy understanding, the joy of finding things out for yourself. The simpleton's mathematical coat of arms. In Euclid we trust, and not the mathematicians. Let a plus b equals c, then multiplying through by a, then b gives 1. A squared b plus ab squared equals a times b times c. Let a equals a to the n, b equals b to the n, c equals c to the n, so that a to the n plus b to the n equals c to the n. Hence, a to the 2n times b to the n plus a to the n times b to the 2n equals a to the n times b to the n times c to the n. Let a plus b plus c equals d. Then multiplying through by a, then b, then c gives 2. A squared times b times c plus a times b squared times c plus a times b times c squared equals a times b times c times d. So for a quadruple where d equals d to the n, we have a to the 2n times b to the n times c to the n plus a to the n times b to the 2n times c to the n plus a to the n times b to the n times c to the 2n equals a to the n times b to the n times c to the n times d to the n. As an intermediate step to 2, we have 3. A squared b plus ab squared plus abc equals abd, where abc is the solution for the triple. For the triple, 3 squared plus 4 squared equals 5 squared. Then 1, 3 to the power 4th times 4 squared plus 3 squared times 4 to the power 4th equals 3 squared times 4 squared times 5 squared is equal to 3,600, which is equal to 60 squared. For the quadruple, 3 cubed plus 4 cubed plus 5 cubed equals 6 cubed. And for the intermediate step, 3, a squared times b plus a times b squared plus a times b times c is equal to a times b times d. Therefore, a squared times b plus a times b squared is equal to a times b times d minus a times b times c. Then 3 to the power 6 times 4 cubed plus 3 cubed times 4 to the power 6 is equal to 3 cubed times 4 cubed times 6 cubed minus 3 cubed times 4 cubed times 5 cubed is equal to 157,248, i.e. 3 cubed times 4 cubed multiplying 3 cubed plus 4 cubed is equal to 3 cubed 4 cubed multiplying 6 cubed minus 5 cubed is equal to 1728 times 91 is equal to 157,248. Considering the increasing number of terms of the binomial expansion of a plus b to the power n, as exemplified by the coefficients given in Pascal's triangle, it is woolly-headed thinking to believe that the multi-term polynomials could possibly collapse to form a triple. The mathematical truth machine, which is of course the quarter squares rule, Euclid's Elements, Book 2, Proposition 8, and where the variables have been modified to suit the Fermat equation. It is self-evident that the position of a, b or c to the power n in the equation is irrelevant, and that the three-term composite output implies no equality between the three variables in the equation. So the composite abc to the power n can be homogeneous, where a to the n plus b to the n equals c to the n, or heterogeneous, where a to the n plus b to the n is not equal to c to the n, for both composites all integer. We see in example 1.1 that the variables which constitute a Pythagorean triple, and therefore an equality, result in the requisite three-term composite ABC all squared. In examples 1, 2, 1, 3, 1, 4, where one term has been replaced by the sum or difference of the other two terms, which give an exact equality, then all three results are equal to one another and to the composite ABC all squared. The quarter squares rule equation is behaving totally rationally, which is only to be expected, since it is, after all, just a rearrangement of the Pythagoras theorem. On this and the next slide, we repeat what we have just done, but with two cubic quadruples, where the smallest term of both quadruples is equal to 1, one of which is positive and the other negative. They are the smallest quadruples in two infinite series, where all the quadruples contain plus or minus 1 as one of the four terms. So we drop the plus or minus 1 term and treat the quadruples as triples, albeit not an exact equality. For examples 2, 1 and 3, 1, we obtain the three-term heterogeneous ABC composite output predicted by the quarter squares rule. For examples 2, 2 to 4 and 3, 2 to 4, we get 6 different outputs, and yet they are all linked to the predicted three-term ABC composite, as shown. We notice that the parity of the difference from the ABC composite are dictated by that of the missing plus or minus 1 term, and therefore reversed for examples 2 and 3. 1. It has been conclusively demonstrated that every triple equality A plus B equals C results in its own unique triple composite ABC, irrespective of whether the exponent is 1 or n. Similarly, expressions of x terms have their own unique composite containing x terms. Irrespective of the number of terms, the development of the algebra results in an inescapable square of every basic term except the initial answer, which is C for the triple and D for the quadruple. 2. The algebra for the ABC composite is easily modified to give the three Fermat-Bateman all-integer quadruple equations of power 1 or 2, which has been fully demonstrated on numerous occasions. 3. Since the cubes only produce all-integer quadruples, of which there are many infinite series, two of which have their last term equal to plus or minus 1, we have via the truth machine demonstrated that an all-integer triple for the cubes is impossible. We have seen that an error of just 1 in the sum is hugely magnified when converted to the composite. 4. And thus we find that what is impossible for the cubes is likewise impossible for all higher powers. Therefore, Fermat's last theorem is true. QED. Corollary. In support of statement 2 for the triple 3 squared plus 4 squared equals 5 squared, we just apply the difference of 2 squares to the three terms of the triple, and we end up with three related Fermat-Bateman quadruples as shown. QEF.